Okay, welcome back. I do apologize for that. We had some issues where the video decided to give up on us, but we are back. Thank you for coming back after the break and hanging out with us. One thing to note before we get started, I think I might have moved a little too fast in some of the labs. So if you do get stuck at all during this, we have at least 5 to 8 people here from Facebook that are here just to help you. So please raise your hand if you get stuck at all or have any questions. I may not stop, but we will make sure that we have people come out to help you because we do want to make sure that you take away a solid amount of information and get a good learning experience out of this. So today, so in this second half, we're going to continue building the framework of what is meant to be, what builds our system at Facebook called FBAR, which allows us to replace a bunch of engineers in a NOC with one engineer and a bunch of software, which doesn't replace your job. So one misconception here is that writing software is going to make you lose your job. It by no means makes you lose your job. It actually makes you much more valuable because now you're writing code to help improve both the morale of the people you're working with, but also allows you to do much more interesting and exciting things. So now we're going to continue though. In the second half, we're going to continue on with another remediation. So the first half, we went deep into regular expressions and Python basics. And in this half, we're going to continue building, looking at another remediation just to give you something else as a building block and some example. So this one, we're going to use specifically a remediation around the idea of looking at link failures and building code to help diagnose link flaps, for example. So if we look at a message like this one, where we see IF down link failure, this is slightly different from the message we saw earlier. The one earlier was about an interface being removed, symptomatic of a bad line card, whereas this one is about a link going down. This message is probably more familiar to you because if you're in a large network, even a medium-sized network, you probably have a lot of links that go up and down randomly, either from fiber cuts, if they're crossing different carriers or different connections, or inside the data center from bad optics or bad cabling. So here, looking at this one, pardon me. So if we extract out, again, with our regular expression matching, we get back the elements of this log line here. So if we look at this, we can start to key off again slightly differently and say if IF down link failure in this error code, let's do something else, for example. But again, coming back to what we used earlier, we need to figure out what the interface is, again, using a regular expression. So if we start to build this live, though, going back into IPython, if you were out of this and you come back into it, there is some stuff that helps save you some time. For example, the list of log lines is actually in memory right now. So you don't have to worry about reopening that log file. Likewise, the regex for the syslog is also in memory. So we can just start running as if we had already written that. So for example, we're working with the second log message right now. So if we do, for example, line equals log lines 1, that's the message we're working with right now for an interface being, or a link going down. So if we get that data back out, for example, we get date stamp, comma, time stamp. And we're just going to now extract back out those variables from the different pieces so that we can start building from this. So error code, comma, error message equals re.match. And so we're calling re.match, again, passing in that regex for the entire syslog. And what I want to get back now is that we have the error code. Cool. So now we can start building this. So assume our code already parsed this out. We can say if that error code is in this remediation, for example, IF down link failure, or again, using lowercase, we could say IF down link failure. And so here, we can start to look at how we can start working on this. So we right now just printed a simple log message of, hey, I found a link failure on switch 2. And let's start to think about how to dissect that. So if we print the error message, If we print the error message, we see that we have a specific interface from this. So to start interacting with this device, let's first think about what commands would we potentially run as a network engineer if we see a link going down. Well, if we look back at just a simple SSH connection, so we were looking at module 5 earlier, and I think in this, just for simplicity's sake, so we're actually looking at module interface 1/4 right now. So let's just debug this as if we were getting this issue as part of being on call. So we might look at things like, for example, show in eth 1/4, and that's going to give us a lot of output, but we might more likely look at, for example, things like CRC counters, or potentially errors. Or maybe resets, even. So in this interface, we see like 2 interface resets. That's probably a stable link, I would say. But if we saw a bunch of resets, that's probably symptomatic of a link flapping. So if we look at our initial remediation, what we were looking at, if we start walking through this, we can write the code to do that debugging for us. So for example, we want to parse out this interface 1/4 from this output to have our code go try to debug for us. So that continues with the same kind of regex that we built earlier, where we say something like this. So again, we use dot to match on anything, followed by a plus to say one or more of anything, until we get to this grouping symbol of 1/4, specifically 1 being represented as /d or /d plus because it may be more than a single digit worth of modules, followed by a / and then again /d plus. And then we close that group with the parentheses here. And then we're trying to match this against the error message here. So if you get a chance, go ahead and try to follow along on this part, where we're trying to create. So for example, if you should have actually, looking back at my history of what I just walked through. So you should potentially have already the log lines in memory with the regex in memory. So go ahead and try to catch up on that part. But what we're getting to here is we want to try to match against this interface. So here, if we look at interface, we successfully matched out Ethernet 1/4 here. So if we print interface.group1, group 1 is going to again represent this first set of parentheses in what we matched against. So now we have 1/4 that we parsed out, which is cool because now we can make our code go run that show interface command for us and try to grab at least the output from it. So we're going to, again, use our handy SSH helper module, which with the SSH connection. So we're going to say output equals ssh.write and pass in the command of show interface. And then we're just going to substitute in the actual number there. So we can do show interface 1/4 here and say dot format of interface dot group 1. I screwed that. So let's actually put our command out first, which might become handy. So if we say command equals show interface eth dot form, and then we use dot format to do again string substitution there to add that interface that we parsed earlier into it. We'll say interface dot group 1 as the thing to put in there. And so if we print command, we should have the same command I typed on the terminal. Show interface eth 1/4. So now let's try to go ahead and run that command against the device. So we have this SSH connection open. Or we don't because I closed my session. So to get that open again, we just do import SSH helper SSH equals SSH helper dot SSH session. And so this is again going to take three things: the device name, switch 1, or this is switch 2 actually, a username and a password. And so we want to run this command now. Output equals ssh.write. And we're going to pass in that command. So if we print the output, we should have output that looks similar to what I ran on the actual terminal earlier. Show interface Ethernet 1/4. In this one, we actually passed in my mock outputs, I actually passed in an egrep command as well to simplify the output a little bit. But what you're getting at, though, is if we did 4-line in output, print line, we're getting back the equivalent of the actual stats that we care about for that interface. Now, I want you to make sure that you follow along on this part. So we don't need to repeat everything that I just did, but if you put together any command that says show interface in it, and you pass show interface to that SSH helper module, you should get back this output. So for example, if you say command equals show interface, you should get back the same output based on the way it's mocked up, which will then make it a little bit easier for you to prototype this without having to deal with the regexes again. So if you are following along and working on the labs, I wanted to pause there for a second to make sure everybody can get back that output so we can start interacting with this. If you have any questions or you get stuck, please, again, raise your hand. So now looking at this from the perspective of writing a remediation to deal with link flapping events, one symptom of this output that we could use to decipher that is the interface reset count. And so while this interface reset count might be different from one platform to another, they each give you some sort of data point that represents this link has gone up and down so many times since X date or when this counter was last reset. In this specific output, we can look at something, specifically the number that says interface resets here, which if you look on, if you were to just print that line, that's this last line that we saw, 229 interface resets. Or in the case of the actual live switch I'm showing, we could see it at the bottom here where it says just simply 2 interface resets on that one. So we can key off of that and then use our friend, again, regular expressions to pull out that data point here. Because unfortunately, this is meant to be read as a human, but we want that piece of data. So what we can do now is as we start to walk through this, since you now have that output, we can start to grab that piece. So what we could do is 4-line in output, we can say reset count equals re.match and build a quick regex against that. For example, we know that the line starts with 229 and then is followed by interface resets. We don't actually know what that number is, and we should not have to know it, or we should not have to care what that number is, but we could use interface resets, the text there, to key off of this. So what we could do is make the regex based on that of /d plus, again, grabbing one or more numbers here, followed by /s plus, and then the word interface resets against the line. And what we actually care about is the /d plus portion here, so we can then put that in parentheses. And so what we could do is see if that matched. Print reset count. Oh, actually, so I screwed this up in that we walked through each line and we reassigned reset count equaling the result of this re.match. We're going to walk through all these lines, and on the ones that fail to match, it will be none. But the one that did match, it will have something. So what we should do is stop running through our loop at that point when it matches. So if we do for line in output, reset count equals re.match, and then if we matched, and note that the indentation here is a little bit off simply because of the way I used up arrow to pull it back up. But if we matched, if reset count, break. So now we should have the reset count. Or not. I think it's actually matching off there's spaces in front of that. Yeah, okay. So this is where you got to be careful because that line actually had some spaces in it. So if you do print output, for example, there's actually spaces there that might be deceiving, which we need to match against since we're doing a match at the beginning. So what we've got now, though, is we have reset count. We've pulled out the number, reset count. And I actually want everybody to kind of get to this point with me. So if you haven't gotten to this already or you were following along, let's go ahead and try this together. So what I had just done, if I hit a history, what I had just done was I walked through each line. So for a line in output, and I had created a regex for this reset count. So go ahead and give that a try. And does anybody remember the way I stopped walking through that loop before? Yeah. Who said that? You get it? Cool. So if we just use the break statement, what is that? Oh, for line and output. Thank you. When you're at a podium, you become much more forgetful. So hopefully, if you're following along, you've now got reset count as this variable in memory, which is our number of resets. Which actually is the matched object. So to get back the individual group, again, group 1. So now we have 229. So we probably want to think about writing some code at this point to compare that against some known threshold. Let's just arbitrarily say that after 10, it's a problem, and under 10, it's not a problem. So what we could do is do a comparison of if, and let's actually just reassign this. So reset count has .group1. Let's just say reset count equals reset count.group1. So now we no longer have the actual match object. We just reassign the individual output to reset count. So now we have 229. So let's say if reset count greater than 10, print warning. Okay, so this actually broke because I am doing something that doesn't make sense in Python. So I get a type error here because I'm actually trying to do a mathematical comparison of a string and a number. It's good to know because when you're using the regex matching, you're actually getting back a string even though it's a number that we're matching against. So what we really want to do, and we see that by saying print reset count. And when I say print reset count, you might wonder, how do I know that that's a string? I saw the type error in my code, but is there a way to know that more specifically? Well, there is. We can use this thing called repr to show us more of what it actually looks like. And here we actually get back it in quotes because it is a string. So when we want to compare this, we actually want to compare the integer version of it such as 2 the 10, because 10 is just an integer here. So by just simply using int and then passing that function of the integer into it, we get back now a way to actually compare this. So at this point, we now say, okay, cool, this is a warning because it has more than 10 interface resets, which you can use based on whatever number you consider a problem in your network. Then we can start writing some code to debug this a little bit more. So if you were on call and you got this issue, what might you look at, for example? I know in my case, or in our case, one of the first things we would look at are stats such as the light levels on the interface if it's a fiber-based interface. So in this platform, I could do that with something like show interface transceiver eth1/4, and show interface eth1/4. So different platforms, different vendors actually flip this order around, which is an interesting tidbit to know. But eth1/4 transceiver details. And this will give me a whole bunch of really useful information for troubleshooting fiber-based links. For example, what is the voltage? But more for this case, what we really care about from our code is this Rx power here. Because we know for certain that after a certain threshold, we're going to have CRCs and interface errors because the link is just not passing enough light to be considered valid signals. Something to know here, actually, as you start to build this code, most of the vendors are actually pretty conservative on this number, and we have found that usually a much tighter or more aggressive threshold is needed when you're writing these kind of remediations way earlier than the alarms or log messages that would be logged by the actual platforms. So in this case, this one's fine. It's got -3.3. But if we look back at our actual slides, we were basing off of one that was much, much worse. So if we look back here, and I'm just hopping ahead. So these slides are, again, what we walk through. So for example, I see only 3 there, but let's say I saw -9, for example, which is within threshold on that platform, but actually a problem or a fault that we would consider where we would want to do something about it and take traffic off of it. So in this case, we want our code to go run a command to inspect that. So this is where we come back to using the on-box utilities to help us, because this is a lot of output right now, which is potentially a large regex to write against. What we could do instead is we could simplify that output, and we could use grep or egrep and only grab based on Rx, for example, because that's the line we care about. And so now we have a much simpler amount of output to write code or route. And so now we can start inspecting this. And what I actually care about is this first column, and I don't care about anything else. The other columns here are actually showing me thresholds. For example, on this platform, it's only going to throw me out a log message when I have power that's worse than -13.97. Well, in Facebook's case, by that point, we have already had an outage or what we call a SEV, if this were an important rack, because our threshold is actually about -7 of where we start taking traffic off the link. So in this case, we want to look at, though, the real power, the current power. And the other numbers we ignore for this. So in this case, we could use other on-box commands if it, for example, had awk or set or anything like that. But this is probably enough to build a regex against, because we only really need to now look at the beginning of this line like that. So if we go back to building our remediation here, we could say now so we should have actually interface reset. We should also have interface in memory. Interface.group 1. So let's just say interface equals that. So if we print interface, we should have just 1/4, which we want to use as this command to go run this light level checking command against. So now let's say command equals show interface eth, and then we'll again substitute that into using these curly brace notation. Transceiver details, and then again using the on-box commands of egrep rx. Again, in this case, this is a case where it's interesting to compare about the uppercasing and lowercasing, because the output in that platform is uppercase with an R, so there's not a clean way to normalize that or non-uppercase it, unless you make it something that you pass degrep where you say uppercase and lowercase, for example. But that's more of just catching ahead as that changes in the output. So, but for simplistic sakes, I would just keep it as like Rx here to match what the actual output looks like. So now to run that command against our dummy device, we could just say output equals ssh.write and pass in that command. Cool. So if you print output, we get back some actual output. I want everybody to actually try this out now, so that way you're still following along and able to interact with this output. So the things that you actually just need to do at this point, we should have an interface that is 1/4, but as long as you write a command that says show interface something with transceiver details, and you pass that into ssh.write, you should get back this pre-staged output of show interface 1/45, for example, where we actually have negative 8.84 as the power, because we're going to use this to actually compare against. In this case, this would be a problem in our environment. So I'm going to take a quick break there. If you get stuck or have trouble, again, raise your hand, and we'll make sure to get somebody to help you. And while we're doing that, are there any questions so far?
Chris Whitfield, Twitter. A couple general questions. First off, I'm assuming that in production there are a pretty long list of regexes you're checking each of your log lines against. Do you run into any real scalability limits on the number of regexes you can check against the volume of syslogs you're getting shipped in on your monitor?
So in production, we actually do, just like you said, it's a large list of regexes that we run against. The way we've solved that is we've just distributed the system. So in our case, we have every single device, including rack switches, which might surprise you. Every rack switch included sends a log message through syslog to a central syslog server. We use Anycast IPs to distribute the load for that. So it's basically BGP injected an Anycast IP throughout the different data centers. So there's not one central syslog server. There's basically different ones in different parts of the data center. But they're built in such a way that they don't have to talk to each other, and they don't have to be central, because what we're doing at the end of the day is we're parsing these log messages locally, and then it's making its way into a database queue, which we won't really dive much into this, but in tomorrow's class we dive much more deeper on the database side. But the individual distributed syslog parsing agents are just parsing their local like cluster or their local. I want to say in each data center we might have like 4 or 5. It's not like one per every part, but there's a handful of them. But then they're just injecting them into the database, and then separate code and separate systems are pulling from the database queue to go act on them.
Okay.
But yeah, that is one of the more painful and one of the slower parts, is that there ends up being a lot of regular expressions of specifically around these different like messages and what to act on.
And do you generally have like just a centralized like one file in Git that has a list of them, or are you doing it with modules?
So what I'm going to show tomorrow is going to be building on this, but what we actually have is we put the regexes in as database entries it's basically into a table of what the regex looks like and what platform it matches against. And then on the actual parsing agent, it just it grabs basically. I don't know if it's. I'm trying to think of how we actually apply it in real time. I think every so often it refreshes, but it basically fetches from the database to build what regexes it's using. Okay. But the actual database entries are strings of the actual regexes.
Got it.
Yeah. Okay. Very good question. And if you have any of these questions like more advanced like that about what we're actually using, free game as well, because I want to make sure that you're definitely engaged and get some usefulness out of this. So cool. So at this point, we should have this output that looks like this, where it's show interface 1/45. So what we want to act on now is start to figure out whether or not the light levels are good or bad, because this is easily 10 minutes of your time if you were on call, and it's not time that you really need to think about. So for example, we can check on this by just looking at this portion of the output. So to grab that, we want to grab Rx power. So let's just start out with Rx power equals none, for example, and then let's say Rx RE equals. And so now what we're going to do is build a quick regex to match against that. So what we can do is /s plus. This is a case where I would actually just now in my code use lowercase and just turn it into lowercase, just in case this changes. So I would look on actually specifically Rx space power. /s plus, and then I would key off of the actual number here of, for example, /d plus. So what I'm building right now is a regex against the spaces in front of Rx power, and then we're looking at specifically the actual exact match of Rx power, and we'll turn it into lowercase as we're evaluating it, followed by, again, spaces. And then the more tricky part is the negative 8.84 dBm, where we've got a negative sign, but then we've got /t plus. But interestingly, we use a dot here. Dot is actually a regex matching character. So we use a / here to say, this is not a regex, this is now an actual exact match. And then /t plus. So at this point, we have the regex defined. And so we can walk through this output and say for line in output, Rx power equals re.match of Rx re against line.lower, so the lowercase version of that line. And then if we matched, if Rx power, let's break out of the loop so we stop trying to look for it. And then if we do print Rx power, we failed to match. So which means I actually have a bug in this. So if we take a look at this real quick. Oh, wait, yes. I think you somebody just helped me fix that. Okay, cool. So this is a good case where it's easy to mix up slashes, for example. So I mentioned earlier that we have a dot in here, which actually means in regular expression sense, or specifically in Python regular expressions, one character or one of anything. And we do not want to actually match on one of anything. We want to match on specifically the dot there. So we use a / to say, ignore this. And so now what we've got is this match was successful. And so if we print rxpower.group and we look at group 1, we now have negative 8.84, which is cool. And I want everybody to actually catch up to this point. So go ahead and try this on your own. Try walking through, for example, for line in output, and try matching that regular expression for the Rx power that we did like this. For everyone that's trying it, did anybody get stuck? Or did you get to the point where you have Rx power? So if we were to print Rx power, again, this is giving me back that matched object. So to access the data from it, we can do rxpower.group1. This is still a little bit tricky because we want to actually evaluate this number, but this number is not a number. Does anybody remember what we used earlier to look at to see if this is actually a number? I think I heard actually both. So there are a couple different ways. One is what we used earlier, the repr command, which prints a more true representation of what we're looking at, meaning that if it's a string, it actually gives us the quote around the string. The other one is potentially type, which tells us the actual type this is. And so in this case, we see that it is the type of a string. So this number, we actually have a decimal notation. So we want to work with it as a float so that we can keep the keep the full decimal. Because if we were to just turn it into an integer, for example, well, we're going to have actually an error here because of the negative, which I think we might have to cut off. Hold on. No, actually float will keep it. So if it were just 8.84 though, without the negative, integer would just cut off and round that for us. With float though, for example, we get back the actual number in a way that we can evaluate it. So if we say our threshold equals, for example, -7, and then we, for example, say if float of Rx power dot group 1, let's say if it's smaller than our threshold, we could, in the simplest sense, print a message here. But, wait. Oh, I screwed that up. So this is where grouping symbols are friendly. So if float, for example, I forgot to close that earlier. So if float Rx power dot group 1 less than threshold, we can print simply a warning message here. But if you start to think about this in a little more advanced sense, you could go a step further here. You could start, for example, you now know, in memory, for example, the Rx power. So you know it's -8.84. You know the device name, for example, switch 2. You know actually the date stamp of when that message came in and the time of when that message came in. So at this point, you could actually start crafting an email that has all of this data in it and send it to either yourself, if you're the appropriate person on your team to solve this, or if you're in a co facility, you could trigger a remote hands ticket here with all of this information. And for example, we know that, and we also have interface. So we know that ETH1/4 on switch 2, based on this data, has power that's -8.84. And based on our code, we could suggest, or in, for example, the message be, for example, if we're opening an email here, message body equals, and we can use triple quotes here now to make it a little bit easier in Python, and say there is an error And so what we could do is craft this body that actually tells the remote hands of what we're asking for. For example, asking them to clean the interface, or clean the interface and the fiber. And then giving them the commands that we use to check as a way to validate, did that fix or solve the problem? Because it could be a number of issues. For example, it could be bad fiber. It could be a bad optic. It could be a bad patch panel even. And we could just simply automate all of that here by just doing this piece. So And so you get the idea here, though. We could actually use Python to send this email directly for us. There's a library called smtplib that you could use. For example, smtplib. Or if you spell it right, SMDP. That allows you to send an email as if from your code. I'm not going to go into details on sending an email, but that's more just to give you some food for thought there of what your code could do. Because at this point, you could simply write a remediation that just simply parses for all the links going up and down to at least grab all these interface counters and these reset counts to kind of automate some of this out of the way. Are there any questions so far on that piece? Cool. So let's start talking about how to keep track of what happened, because it's nice to have code try to fix things for us. But if we start running the same command over and over and start flooding our remote hands with emails of the same issue, that's not too helpful. So we want to keep track of what happened using some sort of persistence here, which would also give us a way later to determine if these are repeat offenders or new events as we see them. So we have a few options though. We can keep track of this in memory using, for example, lists or dictionaries like we saw earlier. We could also keep track of them on disk as a file or as multiple files. And finally, we could use a database. We're actually going to dive into for a bit on the last piece here, using a database as a way to store things. So as you start to build a system like this, you have a few different options, for example. You can start simple with something called SQLite, which is a way to use a database as a file in a way that's very portable in that it stays contained with your code. For example, if you have used any of the original iPods, they actually had a SQLite database on the device as a way to keep track of the library. There was no database server running on the iPod, but it used an actual database schema and wrote to a database using SQLite. That works for small prototypes, but it doesn't scale too well in real environments because SQLite is just using a file, meaning that one person or one piece of code can read and write from that file. But it is a great way to get started. And its syntax is very similar to the real databases out there, like MySQL. Now, to MySQL's advantage, though, as you start to build a system like this, MySQL gives you something such as replication that allows you to distribute the load between what are called read-only slaves and read-write masters. It also allows you to scale, but that brings a course with more infrastructure and overhead. If you are interested, we are running currently MySQL Server on the VM, specifically for the tutorial tomorrow. But it is there with a pre-staged database that to give you some stuff to play with. So as we start to think about this as a database, though, we can kind of look at our log message and call it more generically an event. And we have the same data here that we had previously: a date stamp, a device, an error code, and an error message. As we start to think about storing this with a database, though, we need a few more data points to store, or in database terminology, columns. We need at least a unique identifier, such as the ID number here, which our database is going to handle for us. And we probably want to keep track of some sort of a result to say, were we successful in doing something with this? Did we do something with this? Is the problem still present, or is it a false positive? So we're going to actually start in this section taking a look at this with SQLite, just so that way you have something portable to work with. But as you move up to MySQL, it is a very easy transition to go from SQLite to MySQL from the code perspective. Now, granted, there's some operational differences. So with Python, we have this module called SQLite, for example, that we can import and connect to our database with. Now, connecting to a database here just simply means connecting to a file, because SQLite is going to use a file to represent our database. Before we create that file, though, we need to describe how to create the file. So in database terminology, what we're doing is we're building a schema to describe what we're going to store. And it potentially looks something like this: create table with a table name, followed by the column names. And one piece of maybe trickiness here is that we need to specify what types of data these columns store. So for example, the ID is a primary key that we use to just keep track of unique events. But then we can keep track of the date in the device using these date and text columns. So with SQLite, we open a connection using this SQLite 3.connect method, and we pass it a file name. And we're using this with statement again because we're opening a connection to something, and we just call this session, for example. And so to create our database, we're going to use this session.execute command. And so we're going to now do that piece together live, just to give you some hands-on feel for it. So if you go back to your IPython window, go ahead and try following along with this. Type in import SQLite 3. And once you've done that, let's go ahead and create a variable to represent the file that we're going to save this as. We'll say db file equals demo.db. And it can be just any name. And this will be saved then in the current working directory of this. And so to open that connection to that database, we can say with open, or I'm not, sorry, not with open, with SQLite 3.connect. And if you tab complete, that should complete for you. db file. And then we give that a name. So using, again, our as statement here to assign this to a variable as session. And then let's just try printing session, for example, just to make sure we can connect. And go ahead and try that piece just to make sure that you can get to that. If you have trouble, again, raise your hand and we'll make sure to help you along. And so what we see here is that I'm printing the session object, which is just confirming that I can open that file with the SQL module and I can start doing something with it. So now what we want to do is build the first table that we're going to use to create data into with this, put data into as we start to work on our events. So if we say something like this, and so we're going to create it using just a string. Schema equals and if you use open parentheses and triple quotes, it makes it a little easier in that now everything following is one giant string, which means that you don't have to wrap each line separately. And so what we can do now is say create table events. And so when you type this, the create and table are SQL specific syntax. So they can be uppercase or lowercase, but anything that's specific to your table is case sensitive. So in the case of events, that I'm using lowercase because it will be lowercase. And then after that, we put in parentheses the columns and their data types. So for example, create table events will have an ID column that we'll say is an integer. Also a primary key, which means that we index off of it or we can search by it. And then we're going to say also auto increment, which means that the database is going to handle creating unique numbers for us as we put an entry in the database. And finally, not null, because we need this ID to create something. Then we're also going to have fields that represent, again, our syslog message from earlier, the date stamp, which is of type date, which is a special type in SQLite to represent dates and so on. Then we have our device, which will be a text field, which lets us put in an arbitrary length of text to describe the device name. Same with error code. And if you screw up, just hit Control-C and your up arrow, and it'll let you go back to editing that. And then result, we'll store that as a number, and then have some mapping of these result codes somewhere else to say whether or not this was successful or not. Cool. So the first parentheses now is going to close this parentheses around the columns of this table for events. This is still all one string, though, as we see by the open parentheses and 3 quotes there. So we're going to close that string now with the same. So if we were to print schema, we see the exact same syntax. Now what we're doing here is we're writing code to do the equivalent of what we would do on a database. For example, just to compare what this might look like, I'm going to open another tab real quick. File, open tab. And so I mentioned we have actually MySQL running on here. We're not diving much into that, but I do just want to show you briefly. So just to compare, for example. So in MySQL, we actually have a way to show us how a table was built. So that as we write code, we could maybe use that as an example of writing similar code or recreating the table later. So we can use this like show create table command that gives us basically what we're building right now. The only difference here is this is giving me the MySQL version of it, which is slightly different than the SQLite version. But you start to see that it's basically the same thing. So this shell, what we're doing here, though, is in code, writing the equivalent code in Python. What's nice about that, though, is specifically since we're using SQLite here and it's portable, by writing the code to build the database in Python, our Python code then can consistently reproduce it or recreate it as it moves from one environment to another. For example, if we start in a lab environment, we could check to make sure that our database has the right format, the right schema, and if not, create it for you. Something that the iPod does, for example, when creating the iTunes library, it says if there is no library, go create a basic database already. So here we've got the table. We haven't actually created this yet, but we do have. So what we can do now is bring back that connection or with session, that statement where we connected to the database file as session. And now what we can do is call session.execute and pass it in that SQL syntax. Specifically session.execute, and pass it in specifically that string that represents the command we're going to run against this database file that we have, which should be the variable called schema. And then finally we say session.commit, which actually saves the changes. Because in database terminology, there's ways to check for errors and roll back partial changes to avoid a bad change, for example. And so this threw me an error because I actually already have a database table called events created with this file that's currently on disk. So if I go close that, for example, session.close, if I do ls, for example, which I'm not actually in bash, I'm in IPython, but IPython gives me some of the bash commands, I can see that demo.db already exists. So I should be able to delete it, for example. And now it's gone. So now when I go try to recreate that session.execute should actually work. So what's going on, though, is it's giving me a safeguard to make sure I don't recreate the same table by mistake. So now I should be able to try this again. And if I do ls, you see that earlier I deleted this file, and now it's just been recreated. Now this file is not text, so I can't really cat it and look at it because it is a binary representation that the SQLite module is creating. But it is in the format that the SQLite module understands and lets me query against and update and write against. So now to compare, creating data in this database or this database file, we use this insert statement with insert into. And we simply just say what table to insert into, followed by the column names we're going to insert into, followed by this value statement. I want to call something out here, though, in this example, in that I want to make sure you are aware, if you start to write this kind of code, that I am not using string substitution in this. If you've heard of something called SQL injection, this is exactly how that happens, in that you use .format and arbitrarily substitute some user-provided input into your SQL command. A safer way to go around that is to use the individual API that either SQLite or MySQL gives you, as long as, or whatever database you're using, to handle that replacement. So in this case, for SQLite, I use these question marks to say, there's some arbitrary data I'm going to put in here, but then you pass it in as a separate thing to that execute statement. For example, when I created that session object, I can call x.execute and pass in the SQL string, but then I can pass in a list of things that also get substituted, which then get sanity checked by the underlying module. That's just something good to know as you go to start building bigger and bigger code that might be handling user input for something. Granted, here we're parsing the data, so it's not likely for a user to give us a bad command, such as delete table or drop database. But if you have a CLI command that somehow feeds into your database, that's something that you want to be careful with. So I don't want to bore you too much on just using databases here. So we actually have a library module on here to give you something to run with. So just to show you what is on the USB sticks and what we've given it out as the example code, you'll see a file called db.py here, which is an example based on SQLite. And this walks through what we were just showing of create table events. It also gives you a bunch of helper methods if you want to try prototyping this as you go to build and hack on this. For example, there is a function called insert event, which simply takes in the same types of data we were parsing earlier, of date stamp and timestamp and device name and error code. Likewise, we have which returns back an event ID, for example. And so when you use that, you'll get back a number that represents that event. And there's other methods in here to go fetch events and go update events. And I want to show you this more for food for thought, so as you try to build for this, you have something to start with or something to give you an idea to play with. If you already are familiar with databases, the 201 code that you also have has another DB module, but it's MySQL based, just to give you something to compare against. They're very similar, but it gives you some idea of what the differences might be when you go to move, for example, from SQLite to MySQL if you choose to. And there are other databases out there. I'm not saying one is better than the other. I will definitely say MySQL is better than SQLite, but there are things like MongoDB, and there's all kinds of newer stuff out there that all have different use cases. We at Facebook use MySQL for this kind of system and for a lot of these like transactional systems. And then we have other things that are more for our graphing and real-time systems that are separate. So far, are there any questions? That's going to actually wrap up the database section, because that was more to give you food for thought. But do we have any questions before we continue on? Okay, cool. So I want to go into now talking about some opportunities for improvement, because we walked through this system, and there was a lot of different things we looked at, but it's definitely not a complete system in what I've shown you. This is just the foundations of getting off the ground. But I want to show you in hindsight, though, some things that really stand out as red flags to me that you may see as well or may not have, but I want to just point them out and talk about them for a second. So we have some opportunities for... One second. So, cool, it's back. Sweet. So looking at this, everything I've written so far is in this IPython terminal. And in terms of this idea of scoping, I'm writing what's called globally scoped code right now. And what I mean by that is that all of my code is in the main file. For example, I don't have functions or classes or modules to organize anything. So if I were to actually look at NANOG demo.py, for example, what I mean by this is that as we start walking the actual Python file, instead of just the terminal we were in, things in global space are anything all the way indented out to the left here, the beginning. For example, things like our import statements, things such as even the regular expressions that we have. These are currently in what's called global space. And even this example actually walks through showing everything. For example, it opens the files and it does the parsing. It's not very organized, but it works as a quick hack and a quick prototype. But to compare, as a way to make this better, we can look at the file called nanogdemo.better. It's a slightly different version of it that as we start to scroll down, we start adding functions in here. And what I mean by functions are we say def in some name, where they take in an input and do something. So these functions don't actually run now when the code is called. They have to be run separately. For example, read logs. That code only runs now when we see a command like this, where we say read logs, and we use these parentheses, open, close parentheses. And what's going on there is we're now calling or executing that function. It gives us a way to clean up our code, though, because now instead of running top down, we run based on how these are called. So for example, we could call read logs, which reads the logs once, and then we could call it again. And we could add a while loop to that to start reading them in real time. Now again, not the cleanest way to read your logs in real time, but you could build a very quick hacky way of tail, for example, by recalling the same code without repeating the same code. So again, so we didn't really touch much on functions, classes, or modules here, but they are ways to think about as you build something that's meant to be a system and not just a script. And when I say a system here, FBAR at Facebook replaced probably easily hundreds of people that would have watched a knock. But it didn't just replace those jobs. We replaced those jobs with engineering jobs instead. So instead of having people sitting at a screen that are bored, we have engineers writing more code and making the network smarter and more adaptive and fixing itself faster. So it's not replacing jobs, it's just moving things and making it more exciting. But what I'm getting at, though, is it's a large system of a lot of code, which means that you have a lot of people working on this system. You're not building a system for you to maintain, because code that only you can maintain is useless. You want stuff that your entire team can maintain. So that's where you want to think about organization as you write it, and try to have standards such as how functions are built, how classes are built, and even files. Also, this gets into this idea of testing. We didn't talk much about it. It's actually a pretty advanced topic, but there is ways to write your code in such a way that it tests itself, which is kind of something funny to think about, but it's really important as you start to build really complicated code. Because one way to test code is you just run the code over and over. But if your code involves, for example, rebooting a large network device that might take 10 or 15 minutes to load up, or maybe an hour if it has a lot of line cards, well, that's a really tedious task to test that code. So you could start building code that uses this idea of mocking, which is what we were doing with the SSH module, for example, to go run commands and simulate the expected output so that you know if you go change code or clean up code, you can run these tests to say, did all the other code that I did not actually change get broken, and does it still work? That's where having your code organized a little bit into things like functions come into handy, or make sense. So as we look at organization as well, just one key takeaway point from there is sparse is better than dense. It's been a lifesaver for me, meaning that you can create as many files as you want in Python, and it doesn't care. So there's no reason, for example, to stick all of your remediations into one file. A 10,000 line file is impossible to debug and very scary to add to, whereas 110 line files is much easier to manage. It might look cumbersome in a directory listing, but it is a lot easier to manage over time. So think about that. Now some comments on scaling. So what we built right now is just, again, a prototype, but it's not a real-time system. But in a real world, you would need this to be a real-time system. For example, log parsing would need to be continuous with some intelligence of new events versus old events. A really simple way to do that is you could do a database query to say, does this event already exist before I create it? Or more advanced intelligence based on in-memory, based on what you keep track of. You also want to think about stability as you build something like this that is going to get to the point where you rely on it. For example, persistence is very important. Code crashes and code is updated. You need to be able to support restarting your script without rerunning remediations over and over and spamming all of your on-calls, for example. And note on performance here. One-by-one processing, like we're doing right now for this demo, is okay for a demo. It would not work very well in a real environment, though. because anything where you start to count on this, you want something that can react a bit faster. For example, we're writing SSH commands here, back and forth. Now, granted, those only take maybe 10, 20 seconds to run, depending on how hard of a command it is against the device. But when you start talking about traffic impacting events that you're trying to remediate, for example, interface resets and bad links that cause users to not be able to load, for example, their Facebook feed, you want to be able to respond to that fast. So that's where you can start to think about breaking the script up into different pieces, for example. In today, we were talking about maybe the parser and the remediation as one piece. But it could be two pieces here. The parser as one thing sitting just on your syslog servers, and the remediation code running on something separate. You could also start using, for example, other methods of breaking things up, for example, in running multiple things at a time with some of the more advanced topics in Python and just software in general. And then I have one final appendix section that I kind of just want to give you an idea for food for thought here. It's the idea of separating the backend code from the remediation logic. As you start to have hundreds of remediations, what we were looking at earlier, an if statement, can become quite cumbersome to look at. It could also become quite large. So here's another idea where you could just use a dictionary to your benefit and map, for example, the codes for the actual failures to individual files or remediations that then get called later. It's kind of an interesting magic trick in Python in that modules and functions are actually variables until they're executed or ran. So for example, if I go to my IPython terminal and I just create something to represent this, if I have this function here that represents this remediation, for example, def remediation, and when I run that, I say I print, hi, I am in a remediation. So by just creating that function, I have not run any of that code. I can run that code by saying remediation like that with two open close parentheses. But remediation is actually a variable, in Python terms. So I can use it and treat it and pass it around like a variable as well. So for example, I just printed the variable remediation, which just shows me what name it has, without running the code. So for example, to compare again, using these parentheses lets me run that code. But if I use it without the parentheses, I'm just looking at it or looking at the variable that represents it. So what we could have is a remediation mapping like this. Using a dictionary again, we could say if down interface removed equals the result, and make that run this code called remediation without the open close parentheses. So by just saying remediation there, it's just, other bracket. It's just now the value associated with that code. So then to get back the remediation, I could say remediation equals remediations, and then we just search based on the if down interface removed. So that might look a little tricky, but what I'm trying to get at there is that you can actually separate out and put your mapping of what code to run with the individual error codes simply in a dictionary in some other file, which means that as you start adding to it and changing to it, you don't have to look through all the other code that's doing the parsing and the heavy lifting to make these changes. It just makes things a little bit easier to debug and test as you start to build on it. So that brings us to a close. I hope you learned something from this. I hope you have some questions and enjoyed it. Again, I'm David Swafford with Facebook's NetEng, and I just want to finally say one closing thing of what would you do if you were not afraid? Think about the type of automation you might build. Think about the things that you would do if you had the free time that you could that you could get by writing more code. And then finally, just one final announcement. We have a group on Facebook under Facebook group /NetEdgeCode, which is meant to be a discussion to kind of follow this up. It's not just simply just for us to talk, but it's more for you guys to ask your questions and to give feedback and talk to each other as well. And then the final thing is, again, we're thinking about doing an actual hackathon in the next NANOG. If that's something of interest, please take a look at the poll in that group as well for ideas and dates and all that. But thank you very much. Cool. Oh, and we have time for questions, so any questions as well? Yeah.
Ralph Mullen, Internet Archive. When you're writing remediation code to, like, say, reboot a router or so, how do you test that a mock environment reboots right away? A real router takes some time, and it might be hung during boot or something like that. How can you test that out in a good way?
So the question was about like testing out rebooting of a router. That's actually funny because I have some unit tests for specifically rebooting network switches. So when we're writing these remediations, we do test on real devices. So we will generally test on, we basically have our guinea pigs in the different parts of the network that we make sure that we get the code working from. But in terms of like actual unit tests, for rebooting a router, it's obviously a bunch of different code that gets run. So you have basically what are called unit tests, which then use mocked up versions of these SSH commands. But then you add in arbitrary sleep statements to make it well, I take it back. So one of the tests I do add some sleep statements, but not enough to represent 20 minutes because that would be a lame test. But just enough to slow it down. But basically more of, in that code I'm testing basically after it reboots more of the other pieces of it. So I don't actually test really the reboot in that, like it's a workflow kind of thing. So in our code where we do a reboot of a switch, we'll actually drain the device. We'll do a reboot of it as part of like a code upgrade, and then we'll undrain the device. And then so the test coverage there is more around, does the code before and after rebooting work still? Whereas the reboot code more is just kind of returns back quickly. It is still kind of hard to test that kind of thing because there's a lot of variables at play, if that makes sense.
Hi, Stefan from DENIC.
Yeah.
I'm wondering, what's your operational experience about SNMP versus screen scraping? So what is the advantage?
Oh, yeah, so the big advantage, so in terms of this versus screen scraping, so right now we're just running show commands. Well, SNMP you could also write commands too as well. But what we found is that it's really inconsistent. When you have a bunch of different mixed platforms and vendors, it's really inconsistent the experience of which commands are supported both in read and write on SNMP. So the model, or what basically has kept us sane, is that we use SNMP just for grabbing like interface stats and obtaining the simple graphable things. And then we use screen scraping for the majority of the heavy lifting of both fetching commands. For example, we collect things like BGP data, for example, what BGP neighbors are up, what is the current prefixes. All of the detailed data we just do over screen scraping, and then we stuff it into a database for saving. For the actual break, fix, and remediation flow, though, nearly 90% of this is probably based on screen scraping.
Do you have any experience in comparison of speed and CPU load the difference between SNMP and, for example, if you keep a permanent SSH session open to the box?
That's a good example of something we haven't quite gotten down yet. So our system does all the SSH commands as, the individual remediation will probably do them as one batch connection, but all the different code that's running, for example, the background BGP collections and the background statistics that are collected are all separate. So it's not really batched together, and that actually does cause some problems in terms of CPU load and also in eating up your available V2I lines. So our fix to that is we just rate limit how fast we do some of this stuff. But a better way to do it would be to batch together things that don't need to be real time. For example, we have a separate system that is doing background collections. And that collection system is running things on intervals of every 5 minutes, every 10 minutes, every half hour. but they don't have to be on this exact interval. If we were to rebuild that today, I think we would build it as a way to batch all the things and run at every X interval all of the commands and grab all the outputs separately, but we don't currently right now.
One last question, sorry.
Yeah.
You use Paramiko. I don't like Paramiko because I'm an OpenSSH fan and I like jump host thingy and so on. And my experience with Paramiko is that it doesn't obey the .ssh config. So have you any hint to this?
Oh, that is true. So Paramiko is going to ignore your local SSH config. We actually use a mix of both, calling into bash and running SSH there with OpenSSH and Paramiko. It depends on the tool or the system that's using it. The one advantage with calling into, for example, your local system or bash is that if you're using cert-based auth, you get that for free. Whereas with Paramiko, it's all configured separately. Advantages and disadvantages, but it hasn't been that bad, but it depends on which system we're looking at, though.
Okay, thank you.
Yeah. Yeah.
Hi. So, actually, following up on the SSH question, Chris Woodfield with Twitter. So Juniper has NC client. You've got your own switches that I hope have management interfaces that aren't strictly command line based. How much of this work is actually literally running SSH shell commands on the devices versus other types of device APIs?
So I would say we've actually played with a lot of the vendor APIs, and then we have obviously our own API for the FBOSS side. So on the FBOSS side, we use something called Thrift, which is an open source thing via the Apache Association.
Right.
It follows the standard format of you basically have a way to describe the interface and a way to consume it. If you're familiar with Google protocol buffers, it's quite similar. That's how we interface with our own devices. But for the rest of the network, we still are doing all of the screen scraping. I take it back. First, one of the vendors though, we do XML based, I believe. But we've had a bit of mixed luck on some of the like SSH seems to be our fallback that we always use, that we know works. And then we try out different things, but I would say at least 80 to 90% of stuff is still SSH based.
Yeah. Second unrelated question. Dear God, what device do you have that actually takes an hour to reboot?
If you looked at the box I was on earlier to demo with, if you captured that from the webcast, that actual box takes 45 minutes to come up. It's a pain because on some platforms, every module comes up one by one, and then every interface comes up one by one. So when I say 45 minutes, that time accounts for making sure the interfaces are actually online versus the initial boot up state.
Oh, you're including things like drains and undrains in that?
No, I'm just actually counting hardware. Like there is some platforms we have that literally it does one interface at a time every 2 seconds. And so if you have like 700 interfaces, it just takes forever. Like maybe not 45 minutes, it's at least 20 minutes though.
Okay.
Which is painful. Cool. Well, thank you. And if this is interesting, definitely try to come out tomorrow. Tomorrow we're going to build onto this. There will be no more regular expression pain for tomorrow's session, so that's all over with. Tomorrow we're actually going to be diving more into how to do things in parallel with Python, specifically talking about, for example, threading and doing more than one thing at a time. And we'll be building that all live as well. And then we're also going to be dealing with a little bit of MySQL and then just kind of looking at how to break it into pieces instead of one big script. But thank you again.